Okay. So last class, I'll give two videos yesterday. Both of those were from the electric fields chapter. One was where I was speaking about, it was like a 15-minute video, I guess. And I was talking about spherical conductors in details. So over there, we discussed the graphs of spherical conductors and mostly these, right? And these are the important part, the graphs. You need to understand in details how the graphs look like, the electric field, that is electric field strength graph, and electric potential curves over here for opposite charges and for like charges. So I'll go through those in a bit right now. And the other thing was how charges move through uniform fields. That was the other video. So that was basically this motion of charged particles. So I will now go through these again, no problem. Well, yeah, spherical conductors. Giving you a bit of pointer, a bit of understanding of what spherical conductors are. It's simply, let's say we have a uniform sphere, right? We have some amount of a uniform sphere, a metallic sphere that is a conductor, and I take that sphere, such as this one, and I somehow manage to charge this sphere up with a certain amount of positive charge. So what I do is basically somehow using some sort of an appliance, some sort of a method, I have induced a great positive charge inside this conductor, spherical conductor. Now what that does is, typically speaking, when you had a positive charge such as this, how did we describe its electric field? What was the direction of its electric field? The direction of its electric field was simply outwards, or technically speaking, radially outwards, right? This is how the electric field's positive charge looks like, radially outwards. Now, this charge, we consider it to be a point charge, point particle, which has its fields radially outwards. Now, scale this image, a particle, into a sphere. That is to say that I have multiple one of those charges, positive charges, over here, over here, over here, so on and so forth. So what initially happened, let's say, to paint a picture in your head, I induced some amount of positive charge inside the sphere. You can consider it to be proton for ease of thinking, sure. And what happened was, once the charges were induced inside, they repel each other, right? The charges repel each other because they're like charges. So in this conducting sphere, what happens is they repel each other and take the furthest position away from each other. So they spread apart. They do what? They spread apart. So they evenly spread out through the entire sphere. That is what happens. So every time you put in or induce a charge inside, the charges spread apart the maximum possible distance away from each other. So they go till the surface and accumulate over there, evenly spread out. Even if over here it doesn't seem that they're evenly spread out, consider it to be. Okay. Now, the conversation is, what does this result in? The same thing as it was in gravitational field. When you have a large mass such as this, M, the fields are radially inward, attractive forces. And all of these field lines basically point to a center, which we consider to be the center of the mass, right? And this is the distance from which we take the separation to be. That's great. Similarly, over here, since the charges are evenly spread out, right? They're evenly spread out. What happens is the field lines now, which are outwards, are also radial. And when you draw in the line, they simply point towards the center of the sphere, right? So this is what happens when you have a bunch of charges inside a sphere and they're evenly spread out. They have electric fields which are radially outward, and if extended, will intersect at the center of the sphere. So this is how the field lines for a spherical charge look like. Okay, this is the diagram. Now, these arrows that you see, as mentioned, are the electric fields. And now if you want to understand how the electric field strength varies with distance, we can draw a graph. Typically, if I recall for you, we have this formula of EFS, electric field strength. That is, we remember this, right? And this is a typical y is equals to 1 by x square curve, right? And from this, you understand that if drawn a curve, a graph, it will look something like this. An inverse square curve. Fair? And we consider the 0 to be the position of the point charge, the plus positive charge, right? So this is the position of the positive charge, and as you move away, the field strength decreases. Why? Simple. The electric field lines are more further apart, right? Are more what? Further apart. So field strength decreases with increasing distance as a proportion of square. That's all right, that we understand, but as mentioned over here, I considered it to be a point charge. And the point charge was situated at x is equals to 0, this position. And this is how the graph looks like, right? An asymptote towards the x-axis, and an asymptote towards the y-axis. What happens when I have this conducting sphere where the charges are, summed up on the surface and the field lines, if extended, tend to meet inside? How do I draw the field strength curve from the center like this? So this is the center till the surface. This is the surface till infinity. How does the graph look like, right? So I'm going to show that to you. And I'm going to start off with the thing that we all know till now, that at the surface over here, we have the maximum field strength. Okay. At the surface over here, we have the maximum field strength because the field lines are closest together. Okay. Notice the field lines closest together. As distance increases, it increases. I mean, as the distance increases, the field strength decreases. There, that we understand. So over here, from the surface, call this the surface of the sphere, till infinity, till reaching infinity, it depicts the typical y is equals to 1 by x squared curve, which we are familiar with. And that's fine. But what happens inside the sphere? What happens inside the sphere is the electric field strength is 0. Why? What this means is, if I have any charge inside the sphere located exactly here, somehow I managed to locate a charge inside right over here, positive or negative, does not matter, it will feel 0 repulsion or attraction inside the sphere. 0. That is what it means to have 0 electric field strength inside the sphere. Granted, all of the charges have evenly spread apart and taken a position around the surface of the sphere like this. Granted, that has taken place. If I now put in a charge inside somewhere, it will feel no charge. Sorry, it will feel no force. Why is that the case? So it's a simple answer that let's say I position a charge over here, the yellow dot. Consider that is the position where I have a positive charge, a piece of positive charge. Okay. And even if a charge is positioned over here, it feels zero force. Let's see why. Notice the amount of charge over here. There are 4, let's say, protons over there, or 4 induced charges over there. And over here, you barely have 1 positive charge. Okay. But notice one thing. I'm going to explain this qualitatively, not quantitatively. But let's say I have this positive charge here, and it feels a repulsion from this positive charge. So it's being pushed in this direction. Now, notice one thing. There are 4 positive charges over here, and it also pushes the positive charge down. Right? So there is one charge that is pushing, one charge over here that is pushing our positive charge set inside up, and 4 positive charges up that is pushing my positive charge over here down. And what ends up happening, is both of these forces from up and down are equal. Are what? Equal. How is that possible? How is that possible? Remember, electric field strength is proportional to Q1 divided by separation square. As my separation increases, force decreases. Notice, even though there are 1, 2, 3, 4 charges over here, the distance that they are away from my situated charge over here is more. I'm just explaining right now why the field strength is 0 inside the sphere. That's what I'm explaining. That's where I started. So I'll explain it here. I'm going on with that. So if you've seen the video, you should have an idea. And if not, I'm explaining here again as well. So no worries. So coming back to what I was saying, this situated yellow dot that you see is a positive charge. And this feels a force downwards, repulsion by the 4 positive charges. Although there are 4, but they're further apart. The distance is more. And that force downward equals to the force upward by my 1 positive charge here. Why is it equal, although there's 1 positive charge? Because notice, the distance is less. Distance is less, hence my field strength is more. So both the forces from up, that is 1, 2, 3, 4, on the yellow dot that you see, that is my situated charge, is equal and opposite to the 1 charge that I have over here. So the forces are basically equal. Why? Because the distance compensates for the number of charges. Even though there are 4 charges over here, the distance is larger. So the force up and down on this charge, yellow dot that you see, is equal.
Sir,
Yes.
what are we talking
Yes.
about? Why gravitational field strength is 0 at the center?
Not necessarily at the center, it could be anywhere. So if I have a positive charge here, 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 here. So inside the sphere,
Okay.
why is it 0?
Inside, yeah.
Yeah. That's what we are discussing. So the conversation is, regardless of where you have the charge, doesn't matter, here, 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 the forces on either side are equal. What I have done over here, you can do it with any position. No problem. You can do it with any position. If I have something, if I have something over here and multiple positive charges all around the sphere, and I have a charge over here, you draw 2 lines intersecting it, what you see is there are 2 charges over here close to the dot and 3 charges here further away from the dot. And both the force from either direction, repulsion here, are equal and opposite and cancel out. So what is the net force on my charge situated over here? It is 0. End of conversation, right? So point is, wherever I have my charge inside this evenly conducting sphere, it will feel a net force 0. Hence we say, I don't know why it's lagging. Yeah, that is why we say that inside a conducting sphere that is charged, the electric field strength inside is 0. That is why we say it. Okay. So granted you understand that, you have understood a very important concept. That is how electric field strength varies inside the sphere and outside the sphere. So if you had to draw from the center of the sphere, that is 0, till surface, you draw the electric field strength as 0. And then from the surface till infinity, it is an inverse square curve. So that's great. Oops, what's wrong? Give me a moment. Okay. So, granted you understand that, we move on to something else. That is electric potential. Over here, we want to carry on with the same logic, right? That we discussed upstairs, right? That inside the sphere, the net force is 0, right? Keep that idea in your head because it's going to be helpful over here as well. Give me a moment. So what happens with potential of a charge? What does it mean to have an electric potential EP, not electric potential energy? The work done, let's say, not enough space. Make some space. Right. So let's say I have.
Will we be asked the reasoning as to why the electric field inside is 0?
Why the electric field is inside is 0? No, you won't be asked that. Rather,
I just need to know.
yeah, rather it doesn't even come up in the CIE syllabus much that inside the sphere the electric field strength is 0. Have you seen it? I don't think so. I don't think it's in the syllabus much, but I have just shown it over here. Just know it that inside the sphere it's 0. I guess that's enough. The reasoning I've given is a more qualitative description, so it shouldn't come up in your exam or paper.
Right.
Okay. So now coming back to the electric potential, is what does it mean to have an electric potential? Let's say I bring in 1 coulomb of positive charge, right? That is from infinity to a certain point R. What is the energy or work done on this 1 coulomb of charge? That is electric potential, right? So around the sphere, if I bring, granted this is a positive charge, and I'm bringing 1 coulomb of positive charge from infinity to a certain point near the conducting sphere, I have done some amount of work done, right? Positive work done, rather, because I'm working against repulsive force. So that work done on 1 coulomb of charge is my electric potential at distance r. Consider this distance to be 10 meters. And as I move towards the surface, the work done increases. Why? Notice, as I move towards the sphere's surface, my electric field strength increases. So the force opposing my charge increases as I move towards the surface of the sphere. Valid? So if my force is increasing with the distance closer to my sphere, I'm also doing more work done per unit distance. So that is what you see on the curve. As you move towards the sphere's surface, the work done per unit distance, the gradient, notice, the gradient describes the work done per unit distance, increases, right? So the work done per unit distance increases. However, what happens inside? Hopefully this part you're clear. From infinity to surface, why this looks like this. It's a typical uh, EP, electric potential, is equals to KQ1 divided by R curve. So Y is equals to 1 by X curve till the surface. But what happens from the surface to inside? Why is this constant? Can anyone tell me? Any idea? Why is it constant? So it reaches, let's say, 20 joules and it remains at 20 joules, the electric potential that is, till the center. Why is it constant? Any idea? No? Why do you think the electric potential beyond the surface till the center, that is this much, constant? No clue?
Because it's constant inside the sphere.
What is constant inside the sphere?
The the electric field.
Electric field is zero. The
Yeah.
electric field is inside zero. So why do you think the potential remains constant? You're on some right path, yeah.
Um, the gradient represents the
Electric field strength.
yeah.
Yep. So what you're saying is right. So that's one way to think about it. That the gradient of this, the negative gradient of a potential curve represents my electric field strength, what we discussed last class. So you're bang on that, that the gradient, negative gradient of this is simply zero, right? Negative or positive doesn't matter. The gradient is zero. And I know that electric field strength inside my sphere is zero as well. So that's correct. 100% correct. And if you say that, I'm satisfied, I give you full marks. But there's also, I can also explain it qualitatively. What you said is perfect, that the gradient over here represents zero and electric field strength inside is zero. So by maths and by equation makes full sense. The other way I can explain it to you is going back to the logic of electric potential. It is simply the work done bringing the charge from infinity to a certain point. And what do we know? From infinity to the surface, I face a certain amount of force. Until this surface, I feel the maximum amount of force. That is this amount. So basically, this space under the curve represents the work done. But the moment I go inside the sphere, do I any longer feel any force? Nope. So the moment I cross this horizon and get inside the sphere, my charge, my 1 coulomb of positive charge, no longer does any work done. So whatever work was done in bringing from infinity to the surface was enough. Because beyond this surface, going inside, there is no force. Force is zero. So the work done in going from sphere to the center is zero. That's why it's constant here. Because the work was simply done in bringing the positive charge from infinity to the surface. And from the surface to the center, I do zero work. I don't do any work, which is why it's constant over here. That is it. That is the qualitative way to explain it. What you said is perfect, that the gradient is zero. So it makes sense. If you say that, it's enough. But what I see is also good enough reasoning, that there is no force inside the sphere. So the work done stops at the surface, and that is the net work done that is also carried on inside the sphere. So if 20 joule of work was done, bringing it from infinity to the surface, that's it. And no longer work is done going inside the sphere. So we say the electric potential inside the sphere is also 20 joule, same as the surface. Make sense? Okay. Now, since that part is clear, the other thing is you know about positive charges having a positive curve, that is having the graph on the positive axis, simply because it's a positive charge, right? So if you have a positive conducting sphere, you draw the potential on the positive axis, right? Because if you bring in a positive charge, what is the force? Repulsive. And repulsive forces mean positive electric potential. Okay, so that's why the graph is on the positive axis. And for this, the force really depends on the force curve really depends on which direction you consider positive and which direction you consider negative. So the force one, how do you determine if your graph should be on the positive axis? So for that, you need to determine this rightward as positive and leftward as negative. If this is the key that you have determined, then that means that whatever field line represents rightwards, so the right side of the sphere from the center, so right side represents a positive field or positive force. So we draw it on the positive axis. And inside the sphere, it is 0. So we draw it as 0 over here. And again, inside the sphere, it's 0, such as this inside, right? So it's 0. And over here, it is again going to be a curve on the negative axis. Can you tell me why the field curve is on the negative axis on the left side? That is left of this. Yeah, why have I drawn the field line on the negative axis for this portion of the field lines? Tell me.
Charge is negative.
Sorry, why is it negative?
The charge is negative.
No, it's a positive charge, as in positive sphere. So I'm drawing the curve of electric field strength, right? So on the right side, I've drawn it on the positive axis, and on the left side, I've drawn it on the negative axis. Why?
Is it radially inward?
Yeah, you're on the right path. You're thinking about the direction of arrow. Think more about the direction of arrow.
It's radially inwards, is it?
No, I mean, it's always radially outwards. You're thinking on the right path, that you're thinking about the arrows. Think more about the arrows. And both are radially outwards, but why is the left side one on the negative axis? So if I give you a clue, it is about the direction of that. This direction is rightwards, and I classify it right as positive. And this direction is leftwards, and I've classified left as negative. So if one side of the force field line is on the positive axis, the other will be on the negative axis. Why? Because the direction of force is different. Both are radially outward. Both are radially outward. It is simply that the direction of the field lines are different. This direction of field line is exactly opposite to this direction of field line in different direction. So if I classify right as positive, I have to classify left as negative. That is why the force curve on the right-hand side of the sphere I've drawn on the positive axis, and on the left-hand side of the sphere I've drawn on the negative axis. It's simply the direction of the force or the field lines. Do we get it?
So, what's the definition of electric field again?
Electric field strength.
Yeah.
Yeah. So I'll show it to you. It is simply the force per unit
It's the
charge.
force per unit positive charge, right?
Yes.
So why is it negative here? Even when
So force is a vector quantity, and
yeah.
vector quantities depend on the direction. So the magnitude is same. So if you're talking about the magnitude of the force, they're the same near the surface. Where did I? So over here, whatever the magnitude of force is, it is the same over here. However, since force is a directional quantity, or the direction matters, since the force or the field line points outward, that is in the right direction over here, it is going to be classified as, let's say, positive. And since the force is classified outward but left, it is classified as negative. It is not that the values are different, it is simply the direction it points at is different. That is why. Are we still unsure?
Yeah.
Do we get it? What's happening?
You explain one more time, sir?
So I was saying that, look, over here, when I draw outward, the first thing to understand is a positive charge will have field lines that are radially outwards. Okay, that's the first thing, members. Granted, that is okay, and I draw the radially outward field lines for this positive charge accumulation over here. What we also need to respect is force is a directional quantity or a vector quantity. So the direction of the force determines if it's positive or negative. When I consider the field lines over here, it points in what direction? Right direction, right? And that is why we classify this as positive force. So in the positive axis, because I've classified rightward direction as a positive. Similarly, the radially outward field lines on the left side are pointing in the left direction. So even though the magnitude is the same of the force with respect to distance, it is simply that the direction it points at is different, opposite, which is why it is on the negative axis. Do we get it?
Yeah.
So it's simply
So
the
one
direction.
of the
Yeah.
graph is for the left side and the other one is for the right side?
Yes. So basically, yeah, I have uh, drawn it to scale over here. Okay. So this portion to this portion is the sphere, right? So this is the center of the sphere. This is the radius of the sphere. And then this is the surface of the sphere. This is also the surface of the sphere. This is the maximum force. This is the maximum force over here. And it decreases. The force decreases. One is on the positive axis because it points rightward. The other is on the negative axis because it points leftward. Get it?
Yeah.
So that is it. That is pretty much it. So it's simply the direction of the force. That is why I have drawn it over here. Now, you will see this extensively play out when we get more in depth with the spherical conductor graphs. Till now, we understand the potential curve of an individual positive charge and the electric field strength curve of an individual positive charge or positively charged sphere. Yes. Okay. So now what we want to see is you know what? I'll ask you another question. How do you think if this is my sphere? You know what? I'll ask you guys this. If this is my positive charge sphere, right? Over here. Okay. And I have this is inside the sphere, and this is a positively charged sphere. How do you think on the left-hand side the graph would look like? For this side. I have drawn the right-hand side. How do you think the left-hand side looks like for the potential curve? How would you draw it? Is it the same as this over here? Or is it going to be opposite, as in on the negative axis?
Reflection.
Yeah. Sorry?
It's like reflected on the other side. Yeah.
So you're saying like this?
Yeah, yeah.
Okay. Um, which one do you say? Is it one or two?
Oh. No, it will be two,
Okay, why do you say two?
because it's pointing to the left, on the left side.
Okay, okay. So here's the thing. Now, this is why I have asked it, because I don't know if the question paper will ever be this tricky, but I'm just saying. Force, when you're plotting the force is a vector quantity, and this is where direction matters. When you're talking about potential, what does it talk about? Energy. And doesn't matter if I bring in a charge, positive charge, near a positive charge, from this side to this side, I will do positive work done. If I bring this charge from this side to this side, I will do positive work done as well. Okay. So in either case, I bring it from this side to here, I'm doing 20 joule of positive work because I'm working against repulsive force. If I bring it from this side to here, I am working against repulsive force and I'm doing
This is
20 joule.
electric potential.
This is electric potential. The one we were discussing where inside the work done remains the same. The potential remains the same. Where you said that the gradient of this is zero, hence it makes sense because electric field strength is zero inside the
Sir,
sphere.
we denote
Yeah.
electric field strength as E, right?
Yes, you can. I
And
tend
what
to write it
about
as EFS.
electric potential also E?
Uh, Not really. When I write it as EFS, electric field strength, and EP for electric potential.
All right.
Are you talking with respect to like question paper, how they would write it?
Yeah, like could I write, for example, if I'm writing the formula,
Yeah.
could I write E for both?
I mean, write it as if you're showing the working and you're concerned about how the examiner will mark it for you, if you want to write it in short, write it as EFS, electric field strength, and then write your formula.
All right.
Okay. And when you're writing EP, electric potential, then write it as short as EP. That is what I would do to just save myself in case the examiner doesn't misunderstand. That is what I would do. Okay, fair. So the answer over here, what do you think now? One or two?
It will be one.
One. Perfect. So point is, it's a common misconception that so basically, what you will have is the work done is the same. It doesn't matter which side you're talking about. From you bring it from right to center, or you bring it from left to the center. Doesn't matter. It's the same on either side. Okay. So that being said, that is, we have completed two very important parts, and this is what where I have explained in details. Yeah, I've explained this for you guys. Now, this is where things will start getting a bit complicated. So sit down with a fresh mind. Everything I've discussed till now leads up to this. Okay. Step by step. Here I'm going to set up a system, an isolated system. I have one positive charge and one negative charge. First thing that you notice, do you see the concentric potential curve? That is the circles we discussed in the last class. That what are these? These are simply representing the potential with respect to distance. What does that mean? What does that mean? At this, on this circle, wherever you point, it will have the same EP, electric potential. Let's say plus 20 joule. So bringing a charge from infinity to here, anywhere on this circle, means you have done 20 joule of work done. So that's one of the concentric potential curve. Over here, let's say the EP is 15 volts. Okay, the work done per unit charge, 15 volts. And over here, let's say it is 10 volts. Okay, so as you go away from the center of the charge, it decreases. And with what proportion? 1 by R. Okay, so that's why the spacing increases. Again, advice, always make sure when you draw the concentric potential curve, which you may be asked to, spacing between the successive concentric circles should increase. So you will most likely have to draw 3 circles, each with increasing distance away from the center. Keep this in mind. Okay, keep this in mind. You will see this in Mark's scheme as well. Now,
Sure.
I
Must
yeah,
we also take care to draw perpendicularly to the surface, or
take care to draw perpendicular to the surface. You're talking about the field lines.
Yeah.
Yes, yeah, definitely. That's why I always said radial field lines. So whenever you're drawing the field lines, make sure it is perpendicular. Okay. So this represents a field line, positive charge, let's say, and draw this, square thing to denote that you have drawn a perpendicular line. It may just save you some time. I mean, it's marks, but basically, yeah, it's right. So that is field lined. That is the uh, field line representing field strength, and the circles are the potential circles or the potential curves. Any question on that?
So,
Yeah.
no.
Okay. So uh, one is the potential concentric potential curve. The other is the arrows. The arrows represent what? The field lines. Okay. The field lines. And if I've shown to you how ideally you should draw the field lines, somewhat like this. Okay. You will see this with magnets as well when you study magnetic fields. Somewhat like this. Okay. So this is how the field lines would look like if you would have to draw a proper diagram. Here, this is how the field lines would look like between two
Sir,
different.
in this case, some of them are not, they don't look like perpendicular to the surface, right?
The stem being perpendicular. The stem over here is perpendicular. After that, they curve. So over here, it is perpendicular, and then it starts curving. Are you getting the idea?
Oh,
Yeah. So like from the point over here, it stems as perpendicular, and then it starts bending. That is what really happens. That is what really happens. So yeah, good question. And now, the thing I want you guys to focus on is notice if the field lines are from positive end to negative end. That's good. And what we want to first understand, and this is where I want your attention very carefully, is I want to plot. Hmm. I want to plot the electric field strength versus the distance. And I will do step by step. Okay. Basically, the pink line that you see, yeah, the pink line that you see, this is the resultant electric field strength curve between a positive and a negative charge. Okay.
sir, can you say
And
that again?
the pink line that you see is the
Yeah.
resultant electric field strength curve between a positive and a negative charge. Okay. So our end goal is to come to this resultant potential curve. And I will come to this step by step. How do I get this resultant curve? First thing, the resultant curve again represents the electric field strength, resultant electric field strength. And this represents what force a positive charge would feel if it was, what did it do? If it was directly in between the charges, if it was this close to the negative charge, this close to the positive charge, or any separation, or here, represented
Wait,
as
sir, this is electric potential against distance graph or
electric
electric?
field strength.
So, sir, why did you mention this now electric potential about something?
Electric potential. Oh, I was talking about this. This represents electric potential. These circles that you see.
They represent electric potential.
This orange circle represents how the potential, how the concentric potential circles look like. So, like, as in that is to say, this represents 20 volt. This represents like 15 volt. This represents 10 volt. So the successive drop in energy, the separation increases. So for 5-volt drop in energy, it goes from, let's say, 10 centimeters. Then for the same 5-volt drop, it covers like 10 centimeters. So what this means is, as you move away from the center of the charge, the force is less. So less work is done uh, within the same distance. Basically, if where's the potential curve? It is simply this, right? I'm just denoting this curve with the concentric circle. Okay, I've explained this in the last class, what the potential circles mean. Where is it? Over here. Do you remember this part?
Yeah.
Yeah. So this is where we're talking about the electric potentials around a charge, and we said, well, these simply show the same voltage drop. For having the same voltage drop or work done drop, we have increasing distance. So if I bring in a charge over here, right, it feels less force. So let's say I want to do 10 joule of work done, right? So I go through a larger distance to have the 10 joule of work done. Okay. Now I want to have another 10 joule of work done. I need to do, or I need to go through a small distance because the force has increased now. So this concentric circle, successive concentric circles represent how much you need to travel for the same energy drop or same work done. Do you get the idea?
Yeah.
Okay. So it's just that. And the curve, the graph that you see is of electric field strength versus distance. This, okay? How the force varies. Okay. Okay.
Yeah.
So now, let me also establish this. Right word will be positive, left word will be negative. This is the direction key. Keep this in mind. Okay. Now moving forward, I want to come to this resultant curve. And what does this resultant curve represent? That if I have a positive charge, test positive charge, what force will it feel? And right in the middle, it feels the least force, as in the minimum force between these separation. That is represented by the minima over here. And as I move towards here, it faces or feels an increased force that is towards the minus direction. And if I push it over here, it also feels the same increased force towards the minus direction. So what happens if I have a positive charge situated over here? It will go and sort of settle over here, somewhere over here. Okay, and will sit over here. So if I have a positive charge right in the middle, it just stays stationary over here. And I will prove this to you again when I go to the potential curve. So when I have this situated right in the middle, it has a net force, right? All the minimum, all the minimum, it will be pushed in the rightward direction. So what's the sum of the story? If I have a positive charge right in the middle, it feels the minimum amount of force in the rightward direction. So if I have it over here, drops down below, and then still feels a force, and then rises up to the minus charge. So what the field strength curve represents is the variation the force experiences, a positive charge experiences going from this part to this part. Are you clear on that? Any confusion on that part? What the resultant force represents? Resultant curve represents? Any confusion? Okay. So again, the resultant curve represents the variation of force, sorry, of positive charge fields between this region. So if I write it down, it represents the variation of positive charge experiences between the space of a positive and negative charge. Okay. And also the direction of the force. Since the entire curve is in the positive axis, what does this mean? What is the direction of the force throughout this entire space? Tell me. I've taken rightward as positive, and yeah,
Yeah.
so it will be in the rightward direction. No matter where my positive test positive charge is in between this space from here to here, it will always have a net force in what direction? Rightwards. And that is represented by the field lines. So if you just look at the field lines, that gives you the answer. If I have a positive charge over here, what direction do you think it will travel? It will travel in this direction to the negative charge. Get it? So the field lines give you the direction a test positive charge will travel if kept in this space. Got it? Yeah. Now, how do you get to the resultant curve? Let's go step by step. First, the yellow line. Let's look at the yellow line. Okay. What happens with the yellow? It is the resultant, I'm sorry, it is the field strength. So yellow line is the EFS, electric field strength of positive charge. Okay. So inside the positively charged here, what is the field strength? 0. Okay. Notice this is the center of the charge, and inside the sphere, what is my field strength? 0. Absolutely 0. 0 force. And from the surface of the charge, it is the maximum force and then decreases till infinity. Got it? So the yellow line represents the electric field strength from the surface, sorry, from the center to infinity. From center to surface, it's 0, and from surface to infinity, it looks something like this. Got it? Good. How does it look like on the left side? We just discussed above why it's on the negative axis. Why? Field lines are in what direction? Left. So it's
Upward.
negative. Yeah.
Yeah.
So that's why it's on the negative axis. That is it. And on the center, it's the same thing. It's the same equation. In the center, it is 0. In the center, the field strength is 0. Same equation, same conversation. We understand that. We understand that. Now, let's do that for the negative charge as well. Let's do it for the negative charge. Negative charge inside the negative sphere, what do I have? The field strength is again 0. Same logic as a positively charged sphere. 0. So if you inside it is 0. Okay. And from the surface, maximum force till infinity. Decreases till infinity. Why is this on the positive axis? Why is this on the positive axis? Why is this on the positive axis? Simple answer. The field lines are inwards, my friend. Inwards. And what direction does the field line represent? Positive direction. That is why we have this curve left side of the negative charge, that is the blue line, on the positive axis. However, the right side of the negative charge, what happens? Again, in the center it is 0, but on the right side, notice the field lines are again inwards, but are left direction. Left direction is negative. So we have the same curve as this, but on the negative axis till infinity. Are we confused or are we clear till this point? We good? Are we okay? I'm gonna take that as a yes. If confused, do ask me. No worries. So basically, till now, I have established what the yellow line represents and what the blue line represents. Okay. So the yellow line represents the electric field strength of the positive charge, and the blue line represents the electric field strength of the negative charge. Individually. Now, to represent the resultant electric field strength curve, what do? I add both the curves up. That is what I do. So if I want to find out the resultant electric field strength between the charges, between the space, I add the curves up. So sum of this value plus sum of this value gives me the total electric field strength on the surface of the charge. And I keep doing that for all the values. What do I get? I get these successive points. Okay? I get these successive points. So what am I adding? The electric field strength of both the negative and the positive sphere. Okay? So individually, I'm adding all of the electric field strength values. Once I do that, I get this resulting electric field strength curve. What did I do? I added all the values up. Very simple. I added all the values up. And I got this happy face curve. Clear? That is how we get it. Now, can you do that beyond the region of space over here? Can I do it over here as well? Resultant curve over there? Yes, I can, but it usually doesn't come in your syllabus. What happens is on this side of the curve, the resultant would look something. So I would have to extend this. Oops, something like that. And you add these values. You add both of these values and you have a resultant curve that looks somewhat displaced upwards. Okay, so this is now on the left-hand side of my positively charged sphere. This pink curve represents the resultant electric field strength due to a positive and negative charge existing. So I have added this positive value to this negative value, and I get this pink curve. It just gets displaced upwards. So the yellow line gets displaced slightly upwards. That is the resulting electric field strength due to a positive and negative charge. Same thing over here. If I extend the yellow line, allow me to do that. Yeah. The resultant line looks like this. Okay. So I add the positive value, the negative value, and this blue curve gets shifted up, which becomes resultant field strength curve. Okay. So ultimately, what is my resultant field strength curve or graph? All the pink line. This and this. Okay. This is something that is slightly confusing, and it's a lot of information to digest. And so it's a bit hard of a topic to understand. But take your time, go through this again and again and again. Need a screenshot, take it, keep visiting this until you understand the curves very well. Okay, this represents the force.
Could we have the link class?
Sorry.
Could we have the link for this class?
Yes. This is week 14. Sunday. There you go. It will upload it here. Yeah. Any confusion till now of this? Do you get it? Should I move on to the next thing? Or do you want me to re-explain this?
A bit tricky.
Yeah, it is a bit tricky here. So ultimately, again, if I a bit of a small point and I'll move on to the next potential curve, which is also tricky. This and did I add this? Or this is syllabus? Result potential and electric field curves of two same charges. This is in syllabus. Okay. So ultimately, what I have drawn over here is if I have the resultant, I'm just explaining what the resultant curve means. If I have a positive charge, and granted I have classified right as positive and left as negative. If I have a charge over here, what amount of force should it feel and in what direction? Okay, I have a charge over there. Fair. So let's try and find it out. It is at a separation of, let's say, 2 meters. So what is the value on the resultant curve? Let's see. Over here, let's say this is 2 meters. 2 meters away from the center of the circle. Okay. 2 meters away. What is the resultant force? Let's say it is giving me 10 newtons plus. What does 10 Newton plus mean? That it is feeling a force, 10 Newton of force in the rightward direction. So my positive charge, if placed here, feels a 10 Newton of force in this direction. So towards a negative. And rightfully so, because it gets repelled by the positive charge and attracted by the negative charge. If placed over here, what happens? It is, let's say, 5 meters away from either of the spheres. So this is 0, this is 2 meters, and let's say the center is 5 meters away from the center of positive sphere. So what is the value over here of the field strength? Let's say it is 6 Newton, but positive. What does this mean? This means it feels a force of 6 newtons in the rightward direction, in this direction. So the direction of force has not changed. That is why the entire resultant curve is on the positive axis or in between the spheres. Okay, so it feels the force in this direction towards a negative charge. And why is it minimum if you want to understand intuitively? Basically, the reason the force is minimum right at the center is simple. That the space or the separation from the positive charge is maximum and the separation from the negative charge is also maximum. So the positive charge actually feels the least repulsion from the positive charge and the least attraction from the negative charge, which is why the net force right at the center on a positive charge is minimum, but existent. There is still a force over here because it gets repelled by the positive charge and attracted by the negative charge. Although minimum, but still exists. Okay, so feels a force rightwards. Now, why is it negative on the left side of the positive charge? Because if you have a positive charge over here, okay, granted there's a negative charge over here, no worries. But this positive charge gets repelled by this positive charge. It gets a field of force in this direction. And the attraction of this negative charge is very little. Notice the blue line. This is where it is. Notice the blue line. What is the amount of electric field strength by the negative charge or the attraction in this direction? Very little. The repulsion in this direction is way more. Consider this yellow line to be the force of repulsion or the force in the left direction. Way more. So the resultant force, the pink one, the sum of both these values is this shifted line. So net, it still feels a repulsion in the leftwards direction, right? That is the sum of the story. That is the sum of the story. We're simply adding individual electric field strength of the positive charge and the negative charge, and we get this resultant curve. Okay. So go over this as many times as you wish. No worries. Solve problems. The first thing I will ask you guys to do is solve problems, and you will see that you have a better understanding of this entire story. Okay. So now I will move on to the potential curve, and it is a similar story as according to my electric field strength curve, right? How does the potential curve work? Simple. So if you have a positive charge sphere over here, right, of this much radius, right, and I have a negative charge of this much radius. Okay, same story. Now we will look at this individually. Our ultimate goal is to reach the resultant curve. Okay. Why this looks like this, we'll understand. No problem. But ultimately, one by one, for the positive one, did we not already establish that for a positive conducting sphere, the potential curve looks somewhat like this, right? When did we discuss this? Right now. Where? Over here. Remember what this discussion was? Right over here. We discussed that inside the sphere, the potential value remains constant because whatever work was done to bring a positive charge to the surface remains constant because inside the sphere there's no longer any force. So if 20 joule of work was done in bringing this charge to the surface, the work done remains 20 joule inside the sphere as well because there is no force inside the sphere. So no extra work is done inside the sphere. Okay, that's why it is constant inside the sphere. And it increases in 1 by x relation in bringing it closer to the surface. And why is the left side on the positive axis? Because it doesn't matter where you bring the positive charge from the right side or from the left side, there is always repulsion between the positive charge, the test positive charge, and the analyzed positive sphere. There's always a repulsion. So you're always working against repulsive force. So the work done is always positive. So both the curves are on the positive axis. On the positive axis, right? So since that's the case, both the curves are on the positive axis. So for the electric potential of a positive conducting sphere, we have constant electric potential inside the sphere, and away from the sphere, it decreases by 1 by x. Okay. Granted, you understand that. I replicate the same idea over here for the resultant potential curve. I have a positive charge over here. I mean, not a charge, conducting sphere with radius r. Okay. Inside the sphere, it is constant. Potential is constant. Okay. And as you move away, the potential decreases. Okay. Exactly what we established above. Now, for the negative one, how is it different? We know for a negative conducting sphere, for negative charge, the potential value is negative. Why? If I have a negative charge and I bring in a test positive charge, is it attraction or repulsion? Attraction. And attractive forces represent negative electric potential energy. Okay? If that is the case, that means my EP electric potential of the negative sphere should always be negative on the negative axis because the work done in bringing this positive charge from infinity to near the negative charge is a negative value. That work done is a negative value, similar to our gravitation chapter, attractive forces. So work done is negative. So the energy value is on the negative axis, right? Is on the negative axis. As I move closer to the negative charge, the decrease in energy is more. The rate of decrease of energy is more because force increases near the negative charge and I lose my energy more rapidly, right? So that logic applied. We have the EP, electric potential curve of the negative charge on the negative axis. Because the electric potential energy is negative, the work done is negative, okay? Because it's attractive force between an analyzed negative charge and a test positive charge. And we've discussed this elaborately in last class, okay? Same thing, if I also had to draw it on from the right-hand side, it would look somewhat like this. So it's still on the negative axis. It's just that doesn't matter if I bring a test positive charge from here to here or there to here. I'm always doing negative work done. Okay, I'm always doing negative work done. So point is, I have this hill-shaped potential curve for the negative sphere, conducting sphere. So granted, you're okay with the idea of having this yellow potential curve and the blue potential curve, we can sum it up to have the resultant potential curve for for a positive charge in between them. What work done, what work will be done on the test positive charge in any position in this space? And I'll show that to you. So give me a moment. So if I have a test positive charge, what does my result, by the way, what is the resultant curve? We just sum it up. What do? We sum it up. We sum this value, and we get this red value. This value and this value, we get this point. We add this and this, we get this. 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 You get the idea, right? We sum the EP values of what? Of the positive charge and of the negative charge. And we get the red line. Okay. So the electric potential curve of the positive one and of the negative one, we add up and we get this S-shaped curve. That is a resultant electric potential curve due to two opposite charges existing. Okay. Now look, what does this red line mean? That is the question. What does the red line mean? Let's understand. Well, if I have a positive charge, test positive charge, 1 coulomb of, what is the work done in bringing this? Let's say it's over here. What is the work done in bringing this charge from infinity to this point? It will be some positive value, right? Why will it be some positive value? Because it is near the positive charge and you have overcome a lot of repulsive forces to bring the same positive 1 coulomb of charge over here. Now, what if I am moving away from the positive charge and going towards the negative charge? That means A, I'm being repelled by the positive charge and I'm being attracted by the negative charge. So whatever energy I had to bring it near to the positive charge, overcoming all the repulsive forces, I'm losing all that energy. Because this negative charge is attracting me and I'm moving away from the positive charge. So basically, whatever energy I transfer to this positive charge, test positive charge, to overcome the repulsive forces, I'm losing that energy. That's why you see this energy curve decreasing. And as I move beyond the half point, now my energy over here is 0. zero. It doesn't have any energy, but it keeps getting attracted. So from the 0 joules of energy, it now goes to negative. And you will ask me, what on earth does it mean to have a negative energy? It's the same concept as you had in gravitational field. The meaning of having a 0 joule of energy means whatever energy I had transferred to this positive charge to overcome all this repulsive force has been lost. And now it is going to continue being attracted to the negative charge. And you know about negative charges, about attractive forces, that electric potential energy becomes negative. So it keeps going here and its energy value becomes negative. So it becomes negative. So it keeps losing its energy. Do we get the idea? So basically it's losing all of its energy going from here to here. Okay? So it's basically a loss of energy. Okay? That is the entire point. Any confusion till this point? And your scope of syllabus will basically look at what happens inside or in between this space, not beyond the space. Not over here, not over here. So your syllabus will basically test your knowledge. What happens between this space? Okay. So this is how the electric potential curve looks like. You can also think of this as having, a hill over here and a steep decrease. You'll release a ball over here and it will keep moving down, right? It will fall down till this bit over here that represents the negative charge. So basically, you can consider this S curve to be somewhat of a valley, where if you keep a positive charge, it keeps falling down. So it loses all of its energy, right? So I know it's a complicated topic and it's difficult to understand what's happening over here intuitively. But basically, you have to look at with the lens of the formulas that are given to you and the core definition of electric potential energy, or I mean electric potential. So you draw the curves and the graphs of a positive potential curve and a negative potential curve, and you add them up. Because till now, where did the difficulty come in? When explaining this, and I know that. What you guys are okay with is drawing the potential curves or electric field strength curves individually. The moment you added them up, you get this interesting shape for the electric field strength and for the electric potential. You get a very interesting graph. Comprehending that will take some time. That's all right. That's not a problem. And before even explaining this, I've said this, that you will have a hard time understanding this. That's all right. So now, point is, we have this electric potential curve, which represents the work done on a single 1 coulomb of positive test charge. If placed over here, that is 1 meter away or 5 meter away or 10 meters away from here, these values represent what amount of work will be done on that test 1 coulomb of positive charge. That's it. Okay. Okay. So now, what do we do? This is even more complicated. Till now, if you have any questions, just ask me. Go ahead. Any question till now, you can write it down. You can ask me. Let me know if you have any question till this point. We've seen two graphs where we have opposite charges interacting, and we tried understanding how the resultant electric field strength graph looks like and the resultant electric potential curve looks like. And that graph represents what the force will be on a test positive charge at every position and what the work will be done on a test positive charge at every position. So the potential curve represents what the work will be done on test positive charge, 1 coulomb of charge at every single distance. That is a red line. And this pink line represents what is the net force with direction on a test positive charge or 1 coulomb of charge. Okay. Any question till now? No? All good? Give me a thumbs up if it's okay. Is it all right? Should I move on?
Yes.
Okay. Now, okay. So now what we're going to work with is like charges. So basically we worked with opposite charges, positive and negative. And now what we're going to see is repulsive forces in action. And that is what's unique about your electric fields, that you have attraction and repulsion both. In case of how the electric field strength would look in this case, it's simple, fairly simple. It's the same idea. If I draw for the region in between this space, what do we have? Inside the sphere, the electric field strength of the positive charge is 0. Okay. On the surface, it's maximum and decreases with increasing distance away from the charge. And what direction is the field line individually? Don't think of collective with this. I'll explain what the concentric circles mean and why these are oddly shaped. But practically speaking, for a single positive charge, the field lines are radially outwards. Okay. Radially outwards. Okay. So near the surface, it is maximum. Follow the yellow line. Inside the sphere, it's 0. Near the surface, it's maximum and decreases with increasing, the electric field strength decreases with decreasing rate. So initially the decrease is sharp and eventually the rate of decrease of electric field strength is less. Simply y is equal to 1 by x square relationship. Okay. So that's what we are following. Now, the point is that you're okay with this electric field strength line that represents that of my positive conducting sphere. You're okay with this, hopefully. Now I do the same. And why is it on the positive axis? Because the field lines are outwards and in the right direction. Classifying, again, the key is right is positive and left is negative. Granted, you're okay with this idea. I have my yellow line representing the field strength of this conducting sphere on this side. So the field lines are like this. Granted, there is nothing over here. Forget there's anything over here. So the field lines would look like the white lines, not bent. Now let's say I have another positive charge, same over here. And the field lines would look like this, right? Forget there's a charge over here for now. This is how the field lines would look like, radially outwards. And in what direction? Left. And what have I classified left as? Negative. So now, if I draw the line, on what axis will it be? Negative axis. Because the force is leftwards, and I have classified left as negative. The field lines are leftwards, right? So now inside the sphere, what is the force? 0, as usual. And on the surface, maximum but negative. Why? Because it is leftwards. So I basically draw the field strength curve as usual, simply on the negative axis. Simply on the negative axis, nothing else. Nothing else changed. So now inside this, region of space, what happens? What is the resultant electric field strength? I add these values up. Again, I add the values up. So this plus this, I get this, right? Same thing again, same thing again. I add these, I get this, I add these, I get these, I add this, and I get this. I add this, I get this, I add this, I get this. Okay. So what has happened over here? A few things to note. That number one, EFS, granted, I'm considering both the conducting spheres, EFS is 0 at center, at over here, at center, this point. The force on a 1 coulomb of positive charge at the center is 0. Granted, there are 2 positive charges on either side. And right at the center of it, if I position 1 coulomb of positive charge, it will have 0 force on it, 0 net force on it. Why? Any idea why? Why is it 0 net force right at the center? Why do you think so? Any idea? I have 2 positive charges, one on the left, one on the right, same amount of positive charge. So this is, if this is 10 coulomb, this is also 10 coulomb. So if I place 1 coulomb of positive charge right at the center, why does it have a 0 net force? Why? No? Well, it's simple. I'm talking about the net force. The net force will be 0 because the repulsion from this end is the same as the repulsion from this end. Do we get that? So the repulsive forces are basically equal. It's being repelled by the same amount. From here, it is being repelled rightwards. From here, it is being repelled leftwards. That's the key. So it's being repelled in 2 different directions. So same force in 2 different directions cancel out. So the force in this direction cancel out the force in this direction. And that is why right at the center, the electric field strength is 0. It's 0. Okay. And why does it become negative over here? If I have an 1 coulomb of positive charge right over here, why is the electric field strength 0? Oh, sorry, negative over here. Why is the force on it negative? Because I have classified left as negative. So notice the repulsion from this positive charge leftwards is way stronger than the repulsion by this positive charge rightwards. Why is it stronger? Why is it stronger? Because over here, my positive charge is closer to this conducting sphere. Hence, the repulsion to the left is way more strong. That is why I have a net negative force on the 1 coulomb of positive charge. That's the key idea. The direction of force is the key. So the direction of force on my point charge over here, 1 coulomb of charge, is way more on the left side because stronger repulsion from this, because it's closer to that. Okay, net force is towards the left. That's why it becomes negative, because I've classified the left as negative. That's why the force. This axis is the force axis. Okay, electric field strength. And x-axis is the separation, distance away. And now the concentric circle bit. What does the circle? Why do I have so many wiggly lines over here? Previously, when I was explaining electric potential, I talked about the concentric potential circles. They represent, a single circle represent that everywhere on this point, the potential is the same. That is, if I bring in a positive charge from infinity to anywhere on this point on the circle, same amount of work will be done. That was the key. Now, what happens when you have two positive charges added together? The concentric circles actually add up. So the concentric circles that you had previously, they have combined together. What does that mean? What does that mean? That simply means that if I bring in, let's say, let me give you guys a few values to better help understand. Let's say it is 20 volt, this is 15 volt, this is 10 volt, and this is 5 volt, and this is 1 volt, let's say. So now if I bring in a positive charge from infinity away to anywhere on this curve, I have done, you know how much work for a single positive charge? 5 joule of work has been done because it's 5 volt. What does volt mean? Work done per unit charge. Okay. So if I bring in 1 coulomb of positive charge from infinity to this point anywhere, this contour line that you see, anywhere over here, I have done 5 joule of work on the 1 coulomb of charge. So what happens is when you have positive charges over here like this, the potential concentric circles that you previously had combined together to have these lines. Okay, you'll see this again, somewhat like this. So you see, I have two charges over here, one positive. You see over here, there's one positive charge, another positive charge over here, source positive charge, and this line represents what? 20 volt. This line represents what? 5 volt. This line represents what? 3 volt. So this line, this circle that initially was somewhat like this, and this was somewhat like this, they have combined together. This is a phenomena that we see in real life. So the lines have the contour circles, the lines that you had, the concentric circles that you had combined together. So everywhere on this, what is the work done to bring a positive charge from infinity to here? Anywhere on this line will be how much work? How much joule? 3 joules of work will be done on 1 coulomb of charge. Okay, so that's something we do. See. Fair, fair. So now that is basically what the orange lines represent and why they're combined. The pink lines, the field lines are basically being repelled. I mean, the charges are being repelled. And you will see this in a magnet experiment when you have like poles interacting and you have shrapnels of magnetic material on a A4 paper, right? You put a bunch of paper, you put a bunch of pieces of magnetic material, and then underneath, let's say you put like a north face over here, and then underneath you put another north face. You will see the field lines arrange itself using the shrapnels, using the pieces of the that you have left on the paper, and they will align together to represent the field lines, magnetic field lines, and you'll see that they repel each other, somewhat like this. So this represents the repulsion. The field lines are bent away from each other. This field line is bent away from this field line. Why? Because it's like charges, right? Hence they move away from each other. Okay, so that is what the pink lines represent. So now you have understood what the electric field strength versus distance looks like for like charges. Granted, you understand that. Let's understand the potential curve. Do we understand the potential curve of positive charge? Yes, we do. Inside the sphere, it is constant. Inside the sphere, it is constant for a positive charge. Okay. And beyond the inside or from the surface till infinity, it decreases, keeps decreasing. Again, from the surface till infinity, it keeps decreasing. So what do? We add the values up. This plus this, we get this. This plus this, we get this. Now, one thing to note is this is not exactly a horizontal line. It is somewhat slanted upwards. Okay, somewhat slanted upwards. It is also somewhat slanted upwards. Okay, why? Because is this a straight line? No, this is bending downwards. Okay, so when you add this slanted line with a horizontal line, the resultant line would somewhat look like this. Get it? But if I were to draw, I would draw it somewhat like this. Okay? Somewhat like this. Because this, when you add this, it is a bit slanted. Okay. So it's not exactly a horizontal line. Now you continue doing that for all the possible points. And you know what you see? Right at the center, the potential curve is the minimum. What does this mean? If you leave a test positive charge, near, let's say, over here, and that it gets pushed away, keeps getting pushed away, somewhere over here, it becomes stationary. And it just stays here. It won't move. Why? Because the forces are equal and opposite on either side. Similarly, on the potential curve, what do you see? A happy face curve. So if you keep any ball over here, it will simply drop down and stay stuck at the bottom. Okay. It will just stay stuck over here. Why? Because the force is zero over here. No force. It doesn't move. It doesn't move. It just stays stationary over here. Stays stationary over here. Okay. So again, we have just added the curves up and we get this potential curve, well-shaped curve that you see. And with that, you have completed a very, very, very difficult portion of the electric field chapter. Decently difficult. If you have any conceptual question on this, go ahead and ask. Okay, go ahead and ask. I've completed pretty much everything. Any question till now? Go ahead and ask. Otherwise, I'll move on to the last chapter of electric fields, which is motion of charged particles. This is relatively simple. Okay. Fine. Okay. Motion of charged particles in, yeah, any question?
No.
Okay. So now I'm going to look at the motion of charged particles in uniform fields. What is that? Let's say I have set up a charged plate, right? This is a charged plate which is positively charged, and the positive charge is uniformly distributed. And I have a negative charge plate with a negative charge is uniformly distributed. And what do the field lines look like? From positive to negative. So uniform field lines from positive to negative sign. Okay, these are the field lines. Why positive from negative? That's the convention. And they're uniformly distributed. So the force electric field strength at every one of these positions are equal, same. Okay. So what happens when I launch a positive charge or a proton from here to exactly straight up? What is the motion of this positive charge? It bends towards the negative charge. It does what? The trajectory of this proton is a parabola. A what? It is a parabola. Okay. So as it moves through this space, it bends towards the negative side. Fair. And what happens when I launch a negative one? It gets repelled by the negative side, attracted by the positive side, so it bends upwards. Same logic. Why is this important? Let's see. So a few points to note. The charged particle will take a parabolic trajectory inside an electric field, and the direction is decided by the charge itself. If it's negative, it will move towards a positive plate. If it's positive, it moves towards the negative plate. The electric force acts in the same direction and has the same force for all points. Okay. And the amount of deflection depends on the following properties. These three things are important. If the mass of the charge is greater, the deflection will be less. Okay. So what does that mean? When I see that my charge is getting deflected less, that means I have a heavy mass of charge. So this is valid for, you will, if you study chemistry and spectrometers, you will study this there extensively, where we learn something about mass to charge ratio. You will study this in magnetic fields. I'll teach that to you myself. Magnetic fields is a really long chapter. Anyways, so over there we covered this extensively. A higher mass means it gets deflected less, and this applies more so with ions. Less with to do with electrons or protons, more to do with ions itself. So we understand the mass of ions using this relationship actually as a very, very important relationship between two variables. So we identify ions using this relationship because certain ions, higher charge or same charge, and heavier mass, there are isotopes. So we get to identify those. So there's something called mass to charge ratio. Now, what does less deflection look like? Let's say I have an ion with with let's say +2 charge, +1 charge, and it deflects like this green line. And now I have a heavier charge, but same +2 +1 charge, same +1. This is also +1, let's say, but it's heavier. You know what will happen? It will have a path such as this. Isn't the white line less deflected? Yes, it is. Why the less deflection? Because my new ion that is of same charge but higher mass goes through less deflection. That is why that white line is the path taken. Okay, great. The other thing is, as you increase the charge, the deflection is more. What happens if I have +2 charge with the same, let's say, mass? Okay, same mass +2 charge. What is the path taken? You know what, I'll use a different color. Okay. Right? What's the path taken? What do you think? Very simple. It will simply be way more deflected. Why way more deflected? Because the attraction by the negative plate is more and the repulsion by the positive plate is more. That's the idea. So more charge, more deflection. Get it? Now, the speed is inversely proportional to deflection. So if I have the same charge, +1, same mass, coming in with a higher velocity, it will be less deflected, right? It will simply be less deflected. So it will have a path similar to this, less deflected. Okay, less deflected. Why? Because it needs more time for the force to change its direction, because it has a high velocity in this horizontal direction. So for that high velocity to be decreased, right, it needs more time inside this space for the force to act, same amount of force to act, to change its trajectory completely. Okay. So that's why more speed of the particle means less deflection. 1, 2, 3. Understand these very carefully. Very not too many questions are come from this, but it's important. You don't want to lose easy marks, right? So that is the end of electric fields chapter. Okay, that's the end of electric fields chapter. I have covered pretty much everything. Okay. Yes. So now, all good. Any question till now? No. If you have, feel free to ask. Otherwise, I'll give you guys a small introduction to the capacitor chapter. Are you guys okay with the class on, I'm thinking 1 hour class on Thursday?
Um,
Yeah,
Same time
yeah, same time. Okay.
on Thursday.
Yeah, like I'll start at 3 p.m. British summer time and end at 4-ish.
On Thursday or Friday, sir?
Friday, I won't be able to take the class. I'm going to be on a flight, so I've canceled. If you check the latest routine, Friday and Saturday I can't take the class because be I'll not be on ground. So Friday, Saturday, no. Thursday I'll take a 1 hour class because I have something from 4 to 5 again. So I'll take a 1 hour class if that's okay.
All right.
Okay. So I'll give you guys a bit of a pointer today in capacitance and hopefully finish that in the next class because you guys have some of the people are waiting for the recordings and they have exams in October, November. And October, November starts in mid-October. Physics exam is on 16 to 20 or something. That's why. So we have to finish up quite a bit. Capacitance. Okay. This requires quite the extensive understanding from the electric fields, the entire electric fields chapter. Okay. So granted, so the fundamental of this works coming from a bit of understanding from electric potential energy and understanding how we have energy. The concept of energy in electric fields is important over here. Granted, you understand that, we'll be able to move on with this. Okay. What do I want you guys to recall? The thing I want you guys to recall is, I'll write it here.
They are insulators, right?
Capacitors.
Yeah.
Yeah, inside the capacitors, it's insulating. So basically, there's no medium inside. So you can say that, yep. So it's like, air inside. Usually, we consider vacuum. So when you have the walls of the capacitor, inside we say, yeah, it's insulating because the charges can't move inside from one plate to another. If you have one positive plate, yeah, so then the charges can't really move. So you're right to say that. What happens is we induce charge on the other plate. So when you have a really, let's say this is the positive side, and this is neutral side, okay? This is neutral side. And what I'm doing is I'm accumulating a lot of negative charge over here. You know what happens? This induces a positive charge over here because all the negative charge now runs away. Why? Because they get repelled by the negative charge. What is that? Oops. Because it gets repelled by all the negative charge on this plate, okay? So that is how we create a positive charge over here. So it's insulated over here, right? Charges can't flow directly, it's air over here. Air could be anything, honestly. but let's say it's air over here or vacuum over here. So the charges can't move inside. So the negative charge accumulate over here and induces a positive charge over here. So yeah, you're right. So now, what I want you guys to recall is the idea that you guys have. Let's say you have a positive charge from electric fields, that is, a positive charge and a negative charge. Okay. And they're attracted to each other, right? So if they're attracted to each other, they're stuck together. Hmm, do I not need energy to pull them apart? Yeah. So if they're really close together and their electric potential energy is like, I don't know, some really, really high value, right? Say the electric potential energy of these charges are, let's say, 1000 joules. Okay. Just giving an arbitrary value, random value. Let's say the electric potential of the negative charge is minus 1000 joule, positive charge minus 1000 joule. But now, if I want to transfer my energy to, let's say, move the negative charge away, the electric potential energy of the system, I mean, of either the charges have, let's say, decreased to minus 700 joules. So it has increased, not in terms of magnitude, but in terms of value. That is, it is increasing towards zero. And are you getting where I'm going with this? So as I separated the charges, I transferred my energy into these two charges. So I transferred 300 joule of my energy to separate these two charges, positive and negative. So this separation of charge has stored how much energy? 300 joules of energy. I'm just explaining it to you. These values are not relevant. Yeah, any question?
No.
Okay. So basically what I've done is by separating the charges, I have stored a certain amount of energy. And that is how your phone gets charged, by the way. So if you have I'll give you a very crude example. When you have this power, that means a battery inside, there's a cell inside, the electromotive cell inside. Initially, if there's a zero charge, what does it mean to have a zero charge inside your battery? Basically, all the negative and positive charges are not separated. They're not separated. When I connect this to a cell and plug it into a power supply, it separates all the positive charge to one side and all the negative charge to another. Okay, to this side. Okay, point is, all the charges get separated. Okay, so all the charges have now gotten separated. And this separation of charge has stored the energy for me. And now the battery says 100% charge. Okay, why? Because my power supply has separated the charge and stored energy in the battery. So this is how your battery keeps recharging and discharging. What happens when it discharges? The electrons keep flowing to the other side, and the potential difference between these 2 points becomes zero. Okay, so there is no longer a potential difference between the 2 points because all the charges are now well mixed and the battery shows 0%. Why am I saying this? I'm just giving you an idea of how energy gets stored. A very crude introduction to how energy is stored. Obviously, there's more sophistication and more technicality to it, and you will learn about electrochemistry and chemistry. But yeah, that's the core idea. We separate charges to store energy. That's the core idea. Same thing with capacitors. We separate charges to store energy. Okay. And the thing with capacitors are we store very little energy. Okay. So what are capacitors in essence? I've tried to make it a bit easier on you guys. These are electrical devices. So these are electrical devices used to store energy in electronic circuits. And these are commonly used as backup source of energy in case the power supply fails. Well, the second line, don't take it too literally. It's not like a power bank can restore energy, but more so like when you have a capacitor in a circuit, it gets charged up, like you saw in the battery example. When connected to a power supply, charges get separated, and we have a stored energy inside. Similar with capacitors, we separate charges, and we have stored energy in the capacitor that, let's say, switch is turned off right now, and the capacitor will not discharge whatever energy was stored, it discharges it. So basically, a capacitor stores the energy for some time, right? Separates the charge. The moment the circuit is broken, or you turn off the switch, the capacitor discharges the energy. Okay, that's the core idea. Now I'll show you how it works. These are the common shapes of capacitors that you see or will see. So in circuits, you will see this. Which one is capacitor over here? 1 or 2? Which symbol is the capacitor? 1 or 2?
1.
Yeah, 1. So this is the capacitor symbol.
And number 2 is battery.
Exactly. So this is the cell, battery, power supply. Right. So basically, whenever you have one big and one small line over here, that represents the cell, power cell. And when you have the same sides, that represents a capacitor. The nature of them being similar has to do with both being to an extent energy supply, and both having to do with being to an extent plates. Cell, if you look at a cell, it is also at the end of the day to an extent how plates work. So that's why this symbols look somewhat similar. Okay, that's the reason. But basically, this is the symbol of a capacitor. Okay. Now, how does it work? You can have isolated spherical conductors, or you can have parallel plates. You've seen this as, you had uniform electric fields. One was positively charged, one was negatively charged, right? That's one case. The other is you have spherical conductors where you have one uniform sphere inside and one other sphere outside. So if you look at it, think of it as a cut through the middle or the cross section of two spheres. One sphere inside the sphere, one sphere outside the sphere. Okay. Just look at this as a cut through the middle. Okay. So it shows the intersection, the cross section. So what is this? This is showing that the inside sphere, okay, that you have has an accumulation of a bunch of negative charges. 1, 2, 3, 4, 5, 6, 7, 8, whatever. So a bunch of negative charges are on this sphere, and a bunch of positive charges on the outer sphere. Okay, what have I drawn? I don't know. Bunch of positive charges over here. Okay, what has this done? Basically, in this process of separating the charges, this separation that you see, and if I draw the field lines, look like this. Okay, look like this. So basically, this separation of charge has stored an amount of energy in this capacitor. So this spherical capacitor that you see right now has stored some amount of energy by that separation. Similarly, when you have this is a complete circuit. This is a complete circuit. You have a power supply, a battery, and it connects to a plate, and this plate. Notice one thing very interesting. The positive end of the battery will induce a positive charge on this plate, and the negative side of the battery induces a negative charge on this plate. And I'll explain it in details how this happens. I'll show it to you. I find it very fun to explain, but this is how the circuit looks like. So as the electrons flow from here, electrons flow and store up over here a bunch of electrons, bunch of electrons, bunch of electrons. You know what that does? It pushes away all the electrons from here. So the electrons now start moving here to the positive cell. So what happened? This accumulation of negative charge over here induced a positive charge over here. How? Because it pushed away all the electrons, repelled it. And now it completed the circuit because there is a flow of electron through this wire and completes the circuit. So even though it's insulated over here, or you can say it's there's no medium over here for conduction. No conduction takes place over here. It is induced by repulsion, right? So that's how it works. That's how it works. That's how charge is stored. But by the way, if I have 12 volt, if I have a voltmeter over here, this is checking your knowledge from AS. This cell, let's say, is 12 volts. Okay. What is the potential difference between these two plates? What do you think will the reading be? Okay. What is the reading? Tell me. So this voltmeter says the potential difference across the 12 volt battery is 12 volt. And now what will this voltmeter tell me across the two plates of the capacitor? So this entire thing that you see is a capacitor. What will the potential difference be? Any idea?
0.
Yeah. 0? Okay, sure. So you're saying that the potential difference across these two plates will be 0 volts. Now let's check that idea. Where did I connect the points? Over here, here and here. And I connected over here. And I got a potential difference of 12 volt. Because I connected to the positive side and the negative side. Okay. And I got a 12 volt reading. Now, let's say I connected to here and here. What will the reading be? Should it not be 12? Yeah, because it's just I moved further up the wire. Nothing changed. So if here and here gives me 12 volt across the cell, it should give me 12 volt over here and here as well. It's the same. There's nothing changed. I have not crossed a resistor or anything. It's the same. Now let's say I do it over here and over here. What will the reading be? 12 volts again. So the potential difference across the capacitor will also be 12 volt. Why am I saying that? Why does it make sense? I just showed you by connecting the voltmeter at multiple position that it should be 12 volts. That is one way to think about it. The other way to think about it is, look, why is there a 12 volt potential difference? Because there's a accumulation of positive charge over here in the cell, and there's an accumulation of negative charge over here that creates a potential difference. The potential difference exists because there's a separation of charge inside the battery. There's a potential difference. Okay, that is why there's a PD, there's a potential difference between these 2 points. That is why it's 12 volt. Okay, that defines the potential difference. That is a core definition of potential difference. Now, the same thing when I'm doing across the capacitor, shouldn't it also be 12 volt? Because I am accumulating the electrons over here, and accumulating positive charge is over here. So basically, whatever the potential difference over here is, 12 volt, it will be the same across here. Because all of the charges, electrons go, accumulate over here, repel all the electrons from here, and move it here. So there is a 12 volt of potential difference between these two plates as well. Okay? Same. So in a complete circuit, when you have it, whatever the cell potential is also the potential difference across the plates, across the capacitor, regardless what type of capacitor it is. Okay? The same thing happens when you have a resistor. Okay? Same thing happens when you had a resistor. Oops. So if you have a cell potential of 12 volt over here, what is over here? Let's say a bunch of electrons go and it loses its energy and becomes zero energy over here. Has an energy E and has a zero energy because it went through the resistor. So when you take in the lab a voltmeter and measure it across these 2 points of a resistor, what would the reading be? 12 volts. Okay. So remember Kirchhoff's law? So whatever the supply EMF is, the potential difference across all appliances in a series circuit will add up to the supply voltage. Okay. So now you may ask me that, do I need to study AS physics, electricity? Well, not exactly, because I am like at A2 level, you'll have whatever you need to learn covered in A2 level. So you don't need to extensively study Kirchhoff's law or anything. I will repeat that part for you to remember. But extensively, no, you don't need to study electricity right now for AS. Not at all. Okay. So point is, what was the potential difference across the resistor now? 12 volt. Same logic across the capacitor. I understand some of this is bygones, so no point in remembering, but it's for understanding what's happening over here. So you need to understand how circuits work, though. Okay, you will need to understand how circuits work in this chapter. You will need to understand how resistors work, how we have parallel circuits, series circuits. All of that is coming up. Okay, all of that is coming up. So now the next part, and I will end it with that. All of these capacitors have a marker on them or have an identifier on them. We call that identifier its capacitance. It's what? Capacitance. So every capacitor has an unique capacitance value. Okay. That unique capacitance value denotes something. And by the way, the unit of this capacitance value, we say farad. So the unit of capacitance is farad. Just know that. You will understand it eventually, what it means. So when we have the charge plates, I have a cell potential, 12 volt. And the capacitor keeps getting charged up, or the electrons keep flowing until the potential difference across the capacitor is 12 volt. And that's when the capacitor stops getting charged. What does it mean to get charged? That the accumulation of electron stops increasing on this plate. Or the accumulation of negative charge stops increasing on this plate, and the accumulation of positive charge stops increasing on this plate. That is what it means to stop getting charged. Got it? So now, what the capacitance means is it is the charge stored per unit potential difference on one of the plate. That went over your head, hopefully, because you're not supposed to understand what that means. And I'll explain what it is. Basically, granted, the capacitance has 1 volt of potential difference across the capacitor, right? Think of it as 1 volt of potential difference being applied. And the capacitance value tells you how much charge do I have stored on one side of the plate. Why is that important? Why do I need to know that? Why? Because that tells you how much energy a capacitor can hold. What does that mean? Look, the capacitors don't have an inherent voltage value, does it? No, because whatever voltage you supply to the capacitor, it will have the same voltage across the capacitor. If I supply 12 volts, it will have a 12-volt potential difference across the capacitor. So the capacitor will have the same potential difference as supplied to it. Okay, so let's uniformize the definition and say if 1 volt is supplied to the capacitor to have a potential difference across it, how much charge can it separate? That is what the definition is telling you. How much charge can the capacitor separate? That is the value capacitance denotes. But on one plate. Why on one plate? Because look, if it separates 4 coulomb of charge, negative charge over here, 4 coulomb of negative charge, that indirectly means positive 4 coulomb of charge has been induced on the other side, doesn't it? So do you now say 8 coulomb of charge has been separated? No. You say 4 coulomb of charge has been separated. It is just by default that if you're separating charge, one side will be positive, one side will be negative. You have only separated 4 coulomb of charge. You have not separated 8 coulomb of charge. Okay? Sure, the difference will say 8, but that is not the point. You have separated 4 coulomb worth of electrons on one side, and by default or by indirect effect, that induces the same amount of positive charge on the other side. So you have separated technically 4 coulomb of charge. Okay. Okay. So the capacitance value tells you how much charge you've separated, talking with respect to one side of the plate. Okay. Why is that important? Because I told you guys that denotes how much energy the capacitor can hold. You want to know why? Oh, I mean, you want to know how? Look, it's simple. With 1 volt supplied, if it separates 4 coulomb of charge, right? That means, let's say its capacitance value will be 4 farad. That means it can only separate, or I mean store, let's say X amount of energy. Okay, I don't know the value, I'm just saying. Now, if it separates more charge, let's say 20 coulomb of charge, will it not store an increased value of energy, let's say X, or 4X energy? Will it not store more energy? Yes, it will. Sorry, 5X. Yes, it will. Because it has separated more charge with the same potential difference applied across. So while the potential difference is still 1 volt, it has separated more charge, 20 coulomb worth of charge on one plate, and it has stored more energy. That's the key over here. That's the key over here. It has simply separated more charge, hence stored more energy. So this capacitance value is basically denoting how much energy can my capacitor store? How much charge can it store? Because look, voltage is something I supply it with. So I uniformize it and say, I want to know just across 1 volt, how much will my capacitor store? Okay. So for different capacitors, all I need to know is across 1 volt supplied, how much charge can it separate? If a capacitor separates more charge, that means it will inherently store more energy. And if I increase the voltage, of course, the amount of energy stored will increase as well. But for 1 volt, which one can store more? The one that can separate more charge. That is what the capacitance tells you. And again, remember, the value tells you how much charge is separated on one plate of the capacitor. Okay, that is all I will leave you guys with for today. I've put enough information in your head for one day. I will try and manage to take a class on Thursday, 3 p.m. BST, same time as usual. Okay. That's about it. I'll start from tomorrow with how the circuit works with the capacitor. And you have a heck lot of stuffs, but it can be covered. It can be covered easily. Okay. That's all I will leave you guys with. Any question till now, or I will be ending the class for today. Okay.
Okay.
Okay. All good. So I'll end the class then. Okay.
Yeah.
Okay. Bye bye, guys. See you guys on
Thank you,
Thursday,
sir.
hopefully. No, no worries. Bye bye.